Alrighty, all today we're taking a look at question 5 for homework 5. And for this one, we're trying to find the electrical current induced in a loop of wire surrounding a solenoid. Don't know if that's actually how you pronounce it, but we're going to go with that for right now. So we're given the radius of the solenoid. We're given again, it's turns per meter, right? So that's going to be our lowercase n, right? Because our capital N would just be the number of loops. But this one gives us the loops or turns per meter. All right, so we're given that the current is varied. All right, so 2.1 amps per second is going to be our change in current over change in time. Change in current per change in time, right? The circular loop of wire has a radius of 7 centimeters and a resistance and all this fun stuff. All right, so essentially what's happening is we have our solenoid kind of coiling off in the distance. And we have I'll just use a thicker pencil mark, the loop around it. All right, that goes behind, that comes in front. All right, so the loop is just around it like that. That is a garbage looking drawing, but we're gonna go with it. All right, so we're gonna start by finding the magnetic field as caused by the solenoid. All right, so right, for our solenoid, it's our B equals mu naught N times I, right? We have our mu naught, right? That's just the constant, 4 pi times 10 to the negative 7. Our N is given as I don't know why I'm writing it above it like that. Our N is given as the 3,000 loops per meter. Right, and again, since it's in meters, that's our base units, we're going to stick with that. And our current is given, well, we don't have our current. So is this problematic? Well, let's find out, right? So we don't have our current, but we do have our di dt. So all we did was take the derivative of both sides with respect to t. We differentiated with respect to t, right? So our n, our number of loops per meter, doesn't change with time. So it doesn't matter, that's just going to be a constant. Our 4 pi times 10 to the negative 7 doesn't change with time. Right? So the only thing that's really going to change with time is the current. Right? So there's our di dt. So we differentiate with respect to time. Our magnetic field is going to be changing with respect to time because our current is changing. Right? So that gives us our dB dt. Right? So our mu naught N times di dt. Right? So we just took the derivative without actually taking the derivative. Right? So now I can move the two constants down. Right? And now we're just going to multiply by our di dt, our change in current per time, which is the 2.1. And that's just going to give us our dB dt. How much our magnetic field is changing over time. Cool. So we have a fun new equation for our magnetic flux, right? Same thing as the electrical flux, all that jazz, where it's just going to be our vector times the area times the cosine of the angle between them, right? So if we're looking at our area of the solenoid, right? So we're looking at the flux through the solenoid, right? It's going to be like a circle. It's going around. So our area vector is coming out this way, right? And our magnetic field is also coming the same direction, straight down through the center, right? So our angle between them is going to be 0. Cosine of 0 is 1, so we can just kind of ignore that bit. Fun. Makes it so much easier. But again, we run into the same problem where we don't have B, we have dB dt. So I'm going to take the derivative of both sides with respect to t, which is going to give us our d phi dt, right? Because obviously this is going to change with time because this is going to change with time, right? Because our magnetic field is changing, which again, our dB dt, right? But our cross-sectional area of the solenoid isn't going to change over time, so that can just stay as a constant, right? So now, the fun part is actually plugging all this in, right? So we have a value for dB dt we can plug in. Our area of this cross-section, That's just going to be the area of a circle. All right, so that's going to be 2 pi times the radius, pi times the radius of the solenoid squared. The solenoid is 2.5 centimeters, which is 0.025 meters, right? Always in base units, always in base units, right? So we're going to do our d phi dt is going to equal dB dt times pi 0.025 squared. Cool. Now we have our d phi dt, or d phi dt. Still don't know how to pronounce that one either. That's fine. Right? And the great part about our change in magnetic flux over time is that can get us our electromagnetic field, our induced electromagnetic field. So that's just going to be our negative n d phi dt. Right? Because this is our electromagnetic field of the loop. Electromagnetic field coming through the loop is just the bit that's coming through the solenoid. It works out. Number of loops in our singular loop is just 1. Right? And we can also ignore the negative part. It's fine. Right? It's just going to be our change in flux. That's all that's going to be. Right? So our EMF is just going to be equal to that. Right? That other equation was given in the book, but this one's more applicable right now. So just that. So now we have our electromagnetic field in volts. Right? Because that's all that is. Right? The EMF is just in volts. Fun part about a wire, which is this, it's a loop of wire with a voltage and a resistance. We can find the electrical current pretty easily because we have our old friend V equals IR. Is that Ohm's law or something? I don't remember which law it was. It was a law, so it works, but V equals IR. Solve this real quick for the current just by dividing both sides by R. V over R equals I. We have our voltage, right? That's our EMF. And we have our resistance that was given in the problem, 5 ohms. So that's going to give us our electrical current. So our I, right, if we just solve all this out, it's just going to be the electromagnetic field over 5. Cool. And that's going to give you your answer in amps because we kept everything in base units. Base units always. All right, well, I hope you found this problem, or this video, at least a little bit helpful. Let me know if you have any other problems, any other questions about this problem. Ooh, I'm messing this one up. Let me know if you have any other questions about this problem or any other problem that you want me to explain, and I will do my best to try to explain it because I guess Sydney explains stuff.